Research Pavilion 2015 to 2016 is created by the multidisciplinary team at University of Stuttgart. It involves biomimetics of the sea urchin or echinoids and its subspecies, the sand dollar. The team developed the pavilion based on regular echinoids' plate growth structure, fiber and finger joint connection between elements, and irregular echinoids' double layer segments, and material differentiation. The entire structure weighs 780 kilograms, while covering an area of 85 square meters and spanning 9.3 meters. With a resulting material thickness of 1000 on average, the building has a structural weight of only 7.85 kilograms per square meters. Each segment is made out of 3 individually laminated beech plywood strips, ranging between 0.5 and 1.5 meters in diameter. Their specific shapes and material makeup are programmed to fit local structural and geometrical requirements. The building elements consist of extremely thin wood strips. Instrumentalizing the anisotropy of wood, these strips are custom laminated so that the grain direction and thickness corresponds with the differentiated stiffness required to form parts of varying radii. In this experiment, the wood's bending behavior is shown, as the grain direction varies with respect to the long axis of the element. It also illustrates how the primary grain direction impacts stiffness or resistance to bending. Along the spectrum, ranging from 0 to 90 degrees of the primary grain direction, stiffness decreases as bending flexibility increases. Non-orthogonal grain directions, such as 30, 45, and 60 degrees, result in torsional bending. Thus, the initially planar strips can be elastically bent to find a specific shape pre-programmed into their laminate. In this deformed state, the elements are locked in shape by robotic sewing. In this way, 151 geometrically different elements could be produced, which result in a stiff, doubly curved shell structure when assembled. The textile connections developed for this project allow overcoming the need for any metal fasteners. This project explores robotic sewing to not only join the individually bent plywood strips that form a segment, but also to prevent potential delamination. An industrial robot is employed for both assisting during the assembly and bending of the strips that make up one element, and then locking the pre-assembled segment in shape by sewing them with a stationary industrial sewing machine. During fabrication, the robot first moves the segment through the sewing machine so that the strips are connected. Then it guides the segment through along its edge to secure the laminate and attach the PVC-covered polyester fiber membrane that form the lace connection between segments. The robot and the sewing machine are integrated and controlled through a custom software. This ensures that there is no lateral movement during needle penetration.